Welcome to today's lesson. In this first tutorial, we will graph quadratic functions from vertex form. Here we are in the first half of section 4.2 in our textbooks, and we're talking about graphing quadratic functions. We're going to graph these from three different forms. This first one is vertex form. The vertex form for a quadratic function is the equation that we've already been dealing with in our previous chapter when we were graphing our parent functions. Y equals a times our quantity x minus h squared plus k. So this is vertex form. Some people call it HK form. Remember, the squared part of it is the identifier that this is a quadratic. HK is your vertex. Remember, H is always the opposite of what we see in here, and K is the number that's right out here, whatever the number is. So here's our vertex in our graph right down here. That is our vertex. It will always be HK, and that comes from our vertex form. And the value of A, which is always the number that's being multiplied to our quantity, to our parentheses, this will help us determine our outputs, and we'll work more on that today. We call the graph of a quadratic function a parabola. So these graphs that we've been graphing, these quadratic functions, we call this a parabola. That's the name of the graph. All right, and one other part that we want to talk about, the axis of symmetry. The axis of symmetry is the vertical line x equals h that divides the parabola in half. The axis of symmetry will always be a vertical line for our functions, and that means that it will always be an x equals equation. It happens to always be the value of h. Whatever the value of h is, x equals h will be our axis of symmetry. Some people like to dot that in. It cuts the parabola exactly in half. It's a vertical line. It is the axis of symmetry. So these are the two new parts of our parabola. We'll find the vertex today, and we'll find the axis of symmetry, and we'll practice finding a bunch of other things about this function that we've talked about. So let's look at our first example. I have two graphs for you in this tutorial. It says graph each quadratic accurately, and we'll state the requested information and look at all these things that we can talk about. Most of them are review. So let's go. Y equals negative quantity x minus 1 squared plus 4. Let's first start by finding A, H, and K. I believe that that makes sense. So the value of A is always the number that's being multiplied to our parentheses, which, since I don't actually see that, but I do see a negative sign, must be negative 1. H is positive 1, and K is positive 4. So together, H and K will graph our new starting point. It will move our origin 1 unit to the right and 4 units upward. So that's where I'm going to put my star. Now the value of A, since it's negative, my outputs are going to be the exact opposite. So our regular value of A, which is a 1, would require our outputs to be 1, 4, 9, and maybe 16 if we can get there. Remember, these are all the perfect squares, and that's what happens when we're squaring. So when we input a 1, which means go to 1 on either side of the star, we would output a 1. And when we go 2 on either side of the star, we output 4. When we go 3 in each direction, we would output 9, which is 3 squared, and 4, we'd go 16. But because the A is negative 1, we're going to be multiplying each of these outputs by a negative 1. So now our outputs are actually negative 1, negative 4, negative 9, and negative 16. So when I go to the right one, input a 1, I don't go up 1 this time, I go down 1. When I go to the right 2, instead of going up 4, I go down 4, 1, 2, 3, 4. When I go back to the star always, when I go 3 units to the right, I don't go up 9, I go down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm not going to be able to fit my negative 16. I know that this is exactly a mirror image over here because my axis of symmetry would say so. So I'm going to go left 1 and down 1, left 2 and down 4, left 3 and down 9. Connect all of those into a nice parabola. So now that we have the graph, we can start finding all of the information. Let's start with the vertex. We already had the vertex. It's right here. It's the ordered pair 1, 4. The vertex will always be an ordered pair, so please use your parentheses and your comma. The axis of symmetry will always, at least right now, for functions be x equals, and it'll always be the value x equals h. So since h is 1, x equals 1 is the axis of symmetry. And you can see, if you'd like to dot that in, that's absolutely fine. Here's the equation, x equals 1. That's that vertical line. You can see it cuts the parabola exactly in half. Let's talk about domain. Well, domain is going to be pretty easy this entire chapter since we're talking about quadratics. The domain of every quadratic is going to be all reals. Now we could write it like that, or we could write it as negative infinity to positive infinity, whichever one you like. But the domain is going to be all reals. We are pointing all the way to the left and all the way to the right. So every input has an output, so the domain is all reals. The range is going to change from graph to graph. In this case, the range as low as we go, we always go as low as we go, we're pointing all the way down, so our range starts at negative infinity, and we go as high as we can, which is all the way right up here to the very top of my vertex, which the y-coordinate is 4 units, and that's as high as we go. Since we do include this, because this is a nice closed dot, mine's a nice closed star, we do include it with a bracket. Our endpoints will be included in our range. My next question, x-intercepts. I can call them x-intercepts, or I could call them solutions. I could call them zeros. I could call them roots. X-intercepts are where the graph crosses the x-axis. Here's one of them, and here's the other one. If you want to circle them or box them in or not do anything with them, that's fine. My x-intercepts are negative 1, 0 and positive 3, 0. So negative 1, 0 and positive 3, 0. Those are my two x-intercepts. Those are my solutions. Let's do y-intercept. My y-intercept is where my graph crosses the y-axis. And right now I can see that my y-intercept is right here. That's the point 0, 3. Our functions will only have at most one y-intercept. So let's review some increasing and decreasing intervals. We know that we're increasing when the graph is going upward, sort of like up a hill. I can see that this half of the parabola is increasing. Once we get to the star, we start to decrease the other part, the other half. So we have one increasing interval and we have one decreasing interval. And it all depends on the x-coordinates, which is, of course, that value of h again. So we are increasing from negative infinity. Increasing and decreasing intervals, remember, are always along the x-axis. So we're starting here at negative infinity and we're increasing all the way until we get to an x-coordinate of 1. So our increasing interval is from negative infinity to 1. Remember, we never include endpoints for increasing and decreasing. So there's our increasing interval. Once we get to the 1 on the x-axis, then we start to go down the hill, down the roller coaster. This is the decreasing half. So we're going to be decreasing from 1 the rest of the way to positive infinity. Again, never brackets with increasing, decreasing intervals. And then end behavior, we've done this before as well. What's helpful to do with parabolas, since a parabola, your ends will always be pointing in the same direction. It doesn't matter if we're talking about as x approaches negative infinity, the left end, or as x approaches positive infinity, the right end. What I'm going to do is I'm going to approach both positive or negative infinity. I'm going to use my plus or minus symbol because it doesn't matter which side we're talking about, y will be doing the same thing. So I can use my plus or minus symbol, or you can write it as two separate statements like we've practiced before. In this case, on the left side, y is pointing down. On the right side, y is pointing down. So both sides, y is approaching negative infinity. After this first example, you might start to see some connections, and it also a bunch of these things depend on the values of the vertex. You can see the value of h is 1. That appears in the axis of symmetry, and that appears in our increasing and decreasing intervals. The y-coordinate, the k, is 4, and that appears in our range. So you can see that. Let's do one more graph. And here it is. Y equals 1/2 times the quantity x plus 3 squared minus 4. Let's find A. Let's find H. Let's find K. The value of A this time is 1/2. H is a negative 3. And K is a negative 4. So here's our H and our K, which represent our vertex and our new starting point. To the left 3, 1, 2, 3, down 4, 1, 2, 3, negative 4. So here's our little starting point. And from there, I'm going to use my value of A, which is 1/2. Well, again, our regular outputs for a quadratic are 1, 4, 9, and 16. But in this case, we have to cut them all in half. We have to multiply all those outputs by 1/2. So half of 1 is 1/2. Half of 4 is 2. Half of 9 is 4.5. Half of 16 is 8. These are our new outputs. We're still inputting a 1 and a 2 and a 3 and a 4. We're always doing that from the start. We're always going 1 to the right, 1 to the left, 2 to the right, 2 to the left, 3 and negative 3, 4 and negative 4. Nothing's changing that, but our outputs will change depending on what the value of A is. Since A is positive, we're still going to be going upward, but we're going to be doing half as much. So here's my star, here's my 0, 0. When I input a 1, I go up 1/2. When I input a 2, I go up 2. Not the regular 4, I go half as much. Go back to the star. When I input a 3, that means go 3 units to the right. I output 4.5. 1, 2, 3, 4.5. Back to the star. When I input a 4, 1, 2, 3, 4, actually I don't usually input a 4 because normally when I input a 4 I'd have to go up 16 and that usually doesn't fit. But in this case it does because I'm cutting half of 16 and only getting 8. 1, 2, 3, 4, 5, 6, 7, 8 and that will fit. If I tried to do 5, I normally would go up 25, but in this case half of that, which would be 12.5. 12.5 is going to be a little bit off the graph patch, so I'm not going to require us to do that. Let's understand that symmetry happens here. So if I went half up this way, I'd go half up on this side. If I went 2 up here, I would be going 2 up here. If I went 4.5 up on the right side, I'd be going 4.5 up on the left side. And finally, I went 8 up over there on the right, so now I go 8 up over here. And here's our a little bit fatter, if you will, a little bit wider of a parabola. The 1/2 shrinks it a little bit. Okay, great. Let's talk about all of our pieces. We already had our vertex, -3, -4, so I'll repeat that over here, -3, -4. The axis of symmetry is the equation x equals -3. It's always x equals h. And you can see that 1, 2, -3, there's our axis of symmetry. If you'd like to dot that in, that might be helpful to visualize that you've done this correctly. It should be exactly a mirror image. Our domain, well, we can write that the same way every single time. I'll put both. I don't know which one you like to do. Either one is acceptable. The range changes from graph to graph. Now my lowest point happens to be an actual value. 1, 2, 3, -4. That's the lowest we get. And remember, that's always that y, the k of your vertex. So we start at -4 and we include it. And we're going to go all the way up to infinity. Our x-intercepts, where we cross the x-axis, doesn't look like we cross at a nice spot there. Doesn't look like we cross at a nice spot there. This is going to happen. So what we're doing right now is we're trying to solve these quadratics, but since this one does not cross at a very nice spot, we're going to need another technique. And that's why we have other techniques to solve quadratic functions. So graphing helps us sometimes, but that's really only when the dots are nice, right on the crosshairs, integers. If it doesn't cross at nice spots, we're going to need another method. So we're going to, I'll just put future method right now. we'll learn another way to solve for the exact values of these x-intercepts. We'll just put future method. I'll put that in quotes. That's not the answer. That just means that we're not ready for that yet. Okay, our y-intercept, I see that. Here it is right there. Now remember, that's right in between, and that was exactly 0.5. So you could say 0.5, or I'm going to say 1/2. That's a nice value. Increasing and decreasing intervals, that depended on our x-coordinate of our vertex, which we know was -3. This time our graph starts decreasing from -infinity all the way till we get to the star, which is at the value of -3. So we're decreasing, I'll put that in the decreasing, from -infinity to -3. Once we get to the star, which is halfway, then we start to increase. And we increase from this value of -3 to positive infinity. So -3 to positive infinity. And finally, our end behavior. Since both ends do the same thing, I'm just going to write it as one statement using my plus or minus symbol. In this case, the left side points up, the right side points up, so y goes to infinity on each end. Thanks for watching these two graphs, and we'll practice this more and all the information we can tell about a parabola in class. See ya.